You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. The focus of this session will be on some of the automation tools available with OrcaFlex. There are several tools and features in OrcaFlex designed to improve productivity, and these can be particularly helpful when working with multiple files that are based on existing models. For example, if you wish to analyze a series of load cases with varying environmental conditions, a very common practice when working with OrcaFlex. We can think of automation in 3 distinct areas: pre-processing, to create variations on a base model, batch processing, running multiple analyses, and post-processing, to extract results. In order to introduce the concept of these automation tools, I will demonstrate how we can use them. Firstly, we'll use the pre-processing sheet in combination with a template file to create some OrcaFlex load cases in the form of variation models. We will then utilize the batch processing form to run these load cases and create some OrcaFlex simulation files. And finally, I will use the post-processing sheet to output some results. We will then go back through each step in more detail to learn more. So, let's perform some pre-processing to create a series of OrcaFlex load cases. These will be created as variation models from a base file called basecase.dat. The table on this pre-processing sheet defines the variations in each case, which are wave height and period, riser length, and build-up and main stage duration. The blue row in the sheet contains placeholders which are used in the associated template file referenced at the top, which we can see here if we open the template in a text editor. When run, each load case will be saved as a text data file, with the placeholders being replaced in the files by the corresponding values in the table. I click on the yellow anchor cell, then select Create Text Data Files from the OrcaFlex ribbon. Text data files are subsequently created, and we can open one of these in a text editor to show the naive text replacement of the placeholders. Note that this file only contains the changes compared with the base case, which is referenced at the top. Then we can open one of the files in OrcaFlex to show that it references the base case first and then applies the changes listed in the text file. Next, we will look at how we can process multiple files in an efficient way through the batch processor. When working with small numbers of OrcaFlex files, it is obviously relatively straightforward to open and run them one by one in the OrcaFlex user interface. As soon as the number of files we need to run increases, it becomes important to be able to process these files in a more efficient way. For this, we can use the batch processing form accessed from the calculation menu. We can add multiple files to this form and then run them and save the simulation files automatically. This is particularly useful as it can take advantage of multi-threading. Let's take the OrcaFlex load case files which we just created as variation models and add them to the form before running them as a batch. Once the batch is complete, the status identifies them as such, and we see the 8 files are now joined by their corresponding simulation files in the relevant directory. We'll come back to the batch processing form later through a worked example. Finally, results can be extracted from these simulations by adding instructions to the post-processing sheet, an example of which can be seen here. When processed, the results are output to separate sheets within the OrcaFlex spreadsheet. Let's talk about the files I have just processed. The batch processor can handle any type of OrcaFlex files, be they binary data files or text data files. These particular files are actually a series of OrcaFlex variation models, so it would be helpful to understand what a variation model is, and then we can look at how they are created. In simple terms, a variation model is a form of text data file which references a parent OrcaFlex model and includes in it only the changes from the parent model. The variation model is known as the child model. When OrcaFlex opens a variation file, it first reads the data from the parent model. It then applies the changes specified in the child, that is, the variations from the parent. What this means is that if changes are made to the parent model, those changes will be inherited by all variation models that are based on this parent. Let's look at one of these variation models, which can be done in a text editor, since the variation model is just a YAML text data file. We see that it has only a few lines of data. Firstly, the base file is referenced, which is the parent model on which this variation file is based. In this case, the parent model is a binary data file called basecase.dat. Next, there are 3 data items which have changed in the variation model, 2 of which relate to the environment and 1 to a line, the wave direction and height, and the riser length. Although it has only a few lines of data, a variation model can still be opened in OrcaFlex, since it refers to the parent file for all other data when opening it. Having opened the model, if we go to the environment data form, wave direction and height are highlighted with red boxes. This indicates that these values differ from the parent file and is an automatic change tracking facility built into the program. Likewise, if we open the line data form, the section length value is highlighted with a red box, as well as the number of segments and cumulative values, all of which are directly impacted by changing the line length. That has introduced us to variation models, and we've seen how they can be batch processed. We'll now discuss how they are created. Before that, let's start with the basics and consider how we can create a new OrcaFlex model which is very similar to an existing model. The obvious way to do this in any software package is to open an existing file and use the Save As facility. This can be done in OrcaFlex and will create a duplicate file which you can then make the necessary changes to. The downside to this is that you are copying everything into a new file, even if you only want to make 1 or 2 simple changes. This can potentially lead to issues with file storage space if done on a large scale, and also means multiple models have to be recreated if fundamental changes are made that affect all models, for example changing the water depth. As an alternative, we can create a variation model in OrcaFlex. Rather than creating a duplicate file, we already know that this will instead reference the original model, which is classed as the parent file, with the variation model being child to the parent file, and will only contain the variations. Remember that any changes made to the parent file will be inherited by the child model. We'll start by creating a very simple model to use as a base case, which has the properties listed in the table. Insert a vessel and a line into the model. The vessel can use the default properties and should be placed at the global origin 0, 0, 0. The line should be 210 meters long with 2 meter segmentation, with end A connected to the vessel at 35, 0, -7, and end B anchored at 190, 0, and with a height above seabed of 0. Finally, the declination for end A of the line should be 175 degrees. with infinity end connection stiffness. All other properties are at the default values, and we'll save this file as basecase.dat. Now we will create a variation file, which is done from the File menu and New Variation Model, or Ctrl-Alt and N. You can see that the first step is to specify a parent file, which is the model we've just created. This now creates a new model which looks identical to the parent. Before I make any changes, I'll save the new model. We get the usual Save Data window, but note the selected file type is a YAML text data file, rather than a binary data file. Let's call the new file Variation1. The change we'll make in this very simple example is to move the vessel to a new position. On the vessel data form, change the X position to -10. Before closing the data form, you can see that the X value data control now has a red boundary. Remember that this indicates that the value differs from the parent file. Having moved the vessel, we will also make a change to the line, increasing its length to 220 meters. Again, the section length data control now has a red boundary, as well as the other data affected by the change, namely the number of segments and the cumulative values. The variation file now has two changes when compared with the parent: vessel X position and line length. Let's save this file now and go and have a look at the data. Remember that a text data file can be opened in a text editor. Doing this, I can see a very short data file with only the changes we have made listed, as well as a reference to the base file. This is reflected in the size of the variation file, 1 kilobyte compared to 157 kilobytes for the parent file. As well as viewing the data file in a text editor, we also have a handy tool in the OrcaFlex user interface which lets us look at the changes. From the Model menu, select Edit Data as Text, and you will see the changes as well as being able to edit them. For example, change the line length to 230 meters. The line length increases dynamically, and when we open the line data form, we can see that has also updated. At this point, we are also reminded of a useful built-in tool for comparing OrcaFlex files. From the File menu, select Compare Data, and select the current model and the parent file. We are then presented with a data comparison tool which highlights the differences in this case, only two, as we already know: vessel position and line length. For a small number of cases with relatively simple changes, this method of creating variation files within the user interface can be perfectly efficient. However, this would not be the case for creating large numbers of load cases. We would instead need to consider a more automated means of pre-processing, and for this we can turn to the OrcaFlex spreadsheet. This is a special Excel spreadsheet, part of the standard OrcaFlex installation, and which includes some specific functionality integrated into the Excel ribbon. It is provided as a template file which is stored in the OrcaFlex installation folder within the OrcFxAPI subfolder, as you can see here. You can also access it from the Windows Start menu. Go to All Apps and the Orkina Software folder, and then select New OrcaFlex Spreadsheet. This shortcut creates a new spreadsheet based on the template. As well as some example data, you can see the OrcaFlex tab in the Excel ribbon, which contains a number of different tools and links to the relevant parts of the documentation, should you need help using it. We're discussing pre-processing with text data or YAML files, so that's the sheet we will focus on first, and talk further about how we can automate their creation. There is a pre-processing sheet with an option for a method called batch script, but this is a legacy feature and will not be covered as part of this video. As we have seen with the creation of variation files, the text data file format can be easily viewed and edited in any text editor, as well as through the Edit Data as Text option in the OrcaFlex user interface. We can use this pre-processing sheet to define in one table the necessary changes for a series of variation files we require building, before automatically creating them as individual text data files. We can demonstrate this by using this example table for creating text data files. The table includes data for wave height, wave period, and the durations of the two stages in the model, but we can choose what to change in the creation of a series of load case files. I would like to add an additional data item not present in the table, and I'll come back to how to add this in a moment. Text data files will be created from this sheet and will be saved as YAML files. As with variation files, they will only contain the changes and will reference the parent file, also known as the base file. The first key part of the table is the cell containing text data files, and highlighted in yellow. This is known as the anchor cell. Immediately to the right of this is the reference to a template file, which we will use to create the text data files. This is a text file which we will create in a moment. The blue highlighted row below the anchor cell contains a series of variable names, which will be referred to in the template file. These names can be chosen by the user, and whilst it is not compulsory, we've adopted the convention that they start with a % prefix. Any names can be used, and a naive text replacement will be performed, but we have chosen this convention as the replacement process is very unlikely to find other text that begins with %, thus reducing the risk of errors. Below the variable names are the value rows, and each row defines a unique text data file. The first column is compulsory and defines the file name, and the number of subsequent columns will be determined by the number of changes you wish to make in your variation models. As mentioned earlier, I want to change an additional data item, so we'll add a new column between the period and build-up data. This will be for the length of the riser line, so I will give it the variable name %length. And I'll use the data shown in the table. Note that the values in this sheet can be input directly, as these length values are, but formulae can also be used. For example, the build-up stage has been specified as being twice the wave period, and the main duration 5 times the wave period. Formulae like this can improve the efficiency of creating a pre-processing table. Likewise, you could use formulae for the load case file names, as is the case in this example, which is provided in the template. This automates the inclusion of wave height and period and case numbering based on the row, and allows for easy creation of additional rows. This method uses standard Excel nomenclature, but can be a useful time-saving tool, as we only need to build the first file name and then drag it down to copy the formula and create the rest. I will demonstrate this by deleting all but the first file name, which I will highlight and then explain. The items between quotation marks will be directly input as text, the height and period values by referencing their cell number, and the case number is created and automatically increased by subtracting the row number of the first case from 1 plus the row number. Finally, the ampersand symbols concatenate the separate text strings together. If we drag the first cell down from the lower right corner, we will see that this automatically builds the remaining file names. Note that this can be done without affecting the table formatting by right-clicking and dragging the fill handle and selecting Fill Without Formatting. At this point, when the new text data files are created, the variable names in the template will be replaced by the values defined in this table. We now need to create the template file. This can be done manually by creating a new text file in a text editor and saving it as a YAML file. However, a more convenient method might be to start with the base file and create a variation model in OrcaFlex. We can do this from the File menu, as before, by selecting New Variation Model. We'll select the parent file as the base case, change the stage durations, line length, and the wave height and period. The numbers don't matter at this point, we're just using this method to highlight the variables we need in the template. And then we'll save that as template.yml. Next, we can open template.yml in a text editor. And then we'll replace the values with the variable names used in the spreadsheet table. So for stage duration 1, we'll call that build up. Stage duration 2, duration. Wave height as height. Wave period, period. And line length as length. Before we'll save the file again. As mentioned before, note that the use of the % prefix here is a convention we've adopted. Any names can be used, but we've chosen this convention as the text replacement process is very unlikely to find other text that begins with %, thus reducing the risk of errors. We've only selected 5 variables in this simple example, but others could of course be specified in the same way as additional columns in the table. We now need to save our spreadsheet. The template file can be in a different location, but if that is the case, a relative path will need to be specified. The same applies for the file names in the first column if you wish to save these to a different location. For this demonstration, I'll keep everything in the same folder. We are now ready to create these load cases as text data files. And to do this, we first have to select the yellow anchor cell. Then, from the OrcaFlex tab in the ribbon, select Create Text Data Files. We see a message telling us the files have been successfully created and 8 new files have appeared in the folder. We can open one of these to see that the variable names have been replaced by the values defined in the table. Finally, if we open one of the cases in OrcaFlex, it inherits the properties from the parent file and applies the changes specified. These are again identified in the user interface with a red boundary. In this case, the stage durations on the general data form, on the environment form, wave height and period, and finally, the line length. At this point, I should note that variation files don't have to be made using this tool. We've provided it as a simple way to create load case variation files, but for more complex projects, you might write code to create your load cases, for example, using Python. We've already seen a demonstration of batch processing in OrcaFlex, but let's use the batch processing form again to run these 8 new cases. Click the Add Files button and select the 8 cases. We have a Check Files option, which can verify that there are no issues in the files before they are run, including the option to check statics convergence. The Run Batch button will run the analyses in parallel using the number of threads specified in the Set Thread Count option in the Tools menu, the default being the maximum number of available processors. The thread count can be lowered to reduce the impact on your computer's responsiveness if performing other tasks in parallel with OrcaFlex. This does of course mean the batch will take longer to run. The status indicates whether the simulations have successfully completed, and you can see the simulation files appearing in the folder as they are created. If there were any warnings for completed simulations, such as an Euler buckling limit being exceeded, these warnings can be viewed from within the batch processing form. If you need to update the model, you only need to do this in the base file before rerunning the existing variation files, since the variation files will inherit the changes from the modified base file. As an example, perhaps we need to adjust the seabed depth. I'll open the base file and change this from 100 meters to 90 meters. And having saved the base file, if I return to the batch processing form and run the batch again, the variation files will now all have the revised 90-meter seabed depth. And we should be able to see this by reopening one of the simulation files. Finally, I would like to demonstrate how easy it is to add files to the batch processor using a list file, rather than selecting them one by one. A list file is a simple text file that contains a list of items, in our case, a list of OrcaFlex files we would like to run. This can be very easy to create and could potentially be a great way to progressively build a list of files to run in batch, even if they are not stored in the same folder. It can also ensure you only process the files you want to. I'll create a simple list file now to demonstrate. On the pre-processing sheet in Excel, I'll select and copy the list of file names. Then, in a new text file, I'll paste these file names and save this as a list file. .lst. Back in OrcaFlex, I'll go to the batch processing form, remove the previous files, and then add the list file instead. And this will automatically bring in all referenced load case files for running again. I can also demonstrate the inclusion in this list of a file in a different folder. In the list file, I'll add a new file using the // prefix. And moving to the next level up in the folder, there is a file called test.dat, which I want to run as well. After saving the list file, if I go back to the batch processing form and add this list file again, it brings in that additional dat file. And if I run the batch again, we will see the 8 previous simulation files being run, in addition to the extra test.dat file now being run to completion. The list file method can also be used in post-processing for the duplicating of results for multiple simulations, as we'll see later. Having run a series of load case simulations, the final automation step we will run through now is the extraction of results using the post-processing sheet in the Excel template. This is a table of instructions which, when run, will be processed and the results output to the specified location. The instructions table includes a number of columns. The first refers to the sheet where the results will be output. If a sheet of the given name does not exist, it will be created. The next 2 columns dictate any label and their location. The remaining columns specify the results or data which will be output to the specified sheet. Instructions can be manually entered into the table, but a more efficient means of creating them is via the instructions wizard in the ribbon, and we will use this now to create an example. To start the wizard, we need to select the first empty row in the body of the instructions table, and then click on the wizard. Having done this, if we go to the command option at the top, we can see there are just a few commands available to us. In order to extract some results, the first thing we have to do is identify which simulation they will be from, and this is done using the load command. We will select load and then browse to the first of our load case simulations. Having done this, we can select Accept and Close, which will close the wizard, but we still need to choose our results. So we will select Accept and go to Next, which adds the load command as an instruction on row 5, but keeps the wizard open. Now that we have loaded a simulation, the list of available commands is significantly bigger, and you will see some familiar results-related commands, identical to those you can select in the results window via the user interface. Let's select the time history command. Again, we see some familiar options. Before we come on to those, we'll discuss the labels data at the top. Firstly, we select the destination sheet for the results. If this doesn't exist, it will be created for you. We'll choose to create an initial sheet called Time History Results. Secondly, we specify a destination cell for the label and the actual data, or rather where the data will start. The first time you use the sheet, it will suggest A1 and A2 respectively. A time history result will output a single column of results, the quantity of which will depend on the period selected and the logging interval defined on the Dynamics page of the OrcaFlex General Data Form, which is 0.1 seconds by default. Thirdly, we can specify a label or use the default, which will change based on the result or data selected. We'll choose the line, and we would like to output a time history for effective tension at the hang-off, end A. So, mirroring what we would do in the user interface, we've selected effective tension as the variable, the whole simulation as the period, and end A as the line position. Perhaps we'd like to look at a time history of curvature at the touchdown, in which case we can select Accept and go to Next again, this time selecting curvature as the variable, and touchdown as the line position. Note that the label and output cells have automatically incremented to the next column, B1 and B2. This time we will select Accept and Close, and rows 6 and 7 of the sheet are now populated with the instructions we've just created. We can now process these instructions in order to create the results. This is done by selecting the Process All option, at which point you will see the instructions being processed. Looking at the newly created results sheet, we see 2 columns now occupied with labels at the top and then the raw data below that. These can optionally be further post-processed to another sheet or workbook using the usual Excel facilities for formatting, graphing, etc. for reporting purposes. This is just 2 time history results for 1 load case. We created 8 load cases, so it would be nice to be able to extract the same result for each. This can be done with the Duplicate Instructions form. Let's go back to the post-processing sheet. Here we have 3 instructions, 1 to load a simulation and then 2 instructions to load the particular time history results we're interested in. What we would like to do is duplicate these 3 instructions so that we have 1 copy for each of our load case simulations. To do this, we can use the Duplicate Instructions form. Remember, this form is not for creating load cases or running simulations, since that has already been done. Instead, it is automating the extraction of results from each existing simulation. The main information we need to provide in this form is the set of load case simulation files for which we wish to duplicate the instructions. This can be done by simply clicking on Add and then selecting the files. This is easy if they are all in the same folder, but I mentioned earlier that it is possible to add files using the list method for the duplication of results. As mentioned earlier, list files can be a great way to progressively build a list of files to process as a batch, even if those files exist in different folders. To demonstrate this, I have a list file here, which contains the file names of all the simulations I wish to extract results for. so selecting the list file will automatically bring all those files into the window here. Then we can choose to process these results to different sheets or to a single sheet. If we choose the latter, it's important to specify an offset to avoid each newly processed result overwriting the previous one. Our current sheet has 2 columns of results, so we need at least a 2-column offset. The Duplicate Labels option will include a label for each result. Clicking Duplicate doesn't process the results, but prepares the instructions sheet. We then need to process the instructions again. The progress window shows that multi-threading can be utilized to process results simultaneously. The processing options allow you to change the thread count to reduce the impact on your computer's responsiveness if your spreadsheet contains a large number of instructions. You can also specify if there are dependencies within the results instructions themselves, such that they need to be processed one by one. Obviously, with this option selected, you are limiting the processing to a single thread to ensure that instructions aren't processed out of order. Time history results output a single column of data for each result. Perhaps we need a range graph result as well. This result is likely to require multiple columns of data for each case, which might prove problematic when trying to select a suitable offset in the duplicate instructions form. We are free to have as many post-processing sheets as we want, so it can sometimes be helpful to have a separate post-processing sheet for range graph results, or indeed any other results or data you wish to treat differently. I'll create a copy of the sheet and rename it as Post-Processing Range Graph, and delete the contents up to, but not including the instruction to load the first simulation. Now I can create an instruction for a range graph result. Select the next empty row in the sheet and open the wizard again, this time selecting the range graph command. I will specify a new results sheet called range graph results, which means I can go back to using cells A1 and A2 for the label and output cells. I'll choose riser curvature again as an example, and the results I want are the max and min values and their arc lengths. So 3 columns in total for each load case. Again, we can duplicate these instructions exactly as we did before via the duplicate instructions form. This time we need a column offset of at least 3. If we process these instructions, this creates another results sheet as expected, with 3 columns of data for each load case. These are just a few results, but this shows the flexibility of the spreadsheet for easily extracting results for multiple load cases and preparing the raw data for reporting purposes. It is also possible to write programs to automate post-processing using the programming interface OrcFxAPI, the OrcaFlex application program interface. The easiest way this can be done is using the Python or MATLAB programming languages. The API can also perform many functions that simply cannot be handled by the spreadsheet alone. To learn more about this, we have some resources available on the documentation page of our website, and if you are new to Python, we recommend attending one of our workshops for introducing the Python interface to OrcaFlex. That was a review of some of the automation tools available with OrcaFlex. We are continually developing the program, so please keep an eye on our website and LinkedIn page for further tutorial videos being published.